basically, product and test engineers have to develop custom evaluation platforms for every product to characterize and debug it before data sheets are ready for mass testing. And this is a very time-consuming process and can sometimes take months. It's also very expensive because each evaluation platform needs a lot of parts and a lot of lab equipment. Many of the processes are manual and hence time-consuming as well as cumbersome. This process is very repetitive and not user-friendly. The Universal Evaluation Platform is an elegant solution to this. It's a concise platform which is essentially a lab bench on a board. And it saves engineering time. Time is money. Because product engineers don't have to build a new platform for every product that they build and every version of every product, this saves them a lot of time in terms of debugging the platform itself as well as testing it. It also saves components and lab space. As we can see on the right, we have our Universal Evaluation Platform power supplies, which can be used for fixed as well as variable supply testing. And on the left, we have lab bench equipment to do the same testing. It's universal and reusable like a Swiss knife. It can be used for all products and all versions of all products, and it's one solution for all the testing and debugging needed on the product stage. The features it offers are fixed power supply, programmable voltage supplies, communication protocols, digital signal processing, and user interface.
As Sandra mentioned, one of the features that we built into the Universal Evaluation Platform was fixed and adjustable power supplies. These consisted of a couple of subsystems providing common voltage rails, both for CMOS logic components that you see in almost every product today, such as 5 volts, 3.3 volts, 2.5 volts, and 1.8 volts. We have very nicely regulated rails for that. And then we also have an adjustable supply for testing edge cases where parts might be performing under poor power quality conditions or the like. Here's an example of our fixed power supply schematic. We see here we have it's built upon a linear regulator. That regulator we've chosen because it provides a reasonable output regulation level under load. We've actually spec'd out all of our rails to perform at 1 amp at their respective voltages. And then we've got this broken out into 4 channels, so we have 1 rail each for common logic levels. We'll move into our adjustable power supply here, breezing through this. We again have a system based on a linear regulator, and this is adjusted by a digital potentiometer. This then moves over, we'll talk about this in a little bit, to a SPI module built upon our FPGA for the control. And here we can just see an example of how the adjustable power supply is performing. We see a nice linear decay there on our versus our SPI code, which is our input to our digital potentiometer. This is exactly what we wanted to see. We have about 20 millivolts per step, so quite a bit of resolution as far as giving our device under test the power it needs.
We had 3 digital communication protocols on this evaluation platform: SPI, UART, and I2C. The reason for this was that we wanted to communicate with a large variety of products. So the first communication protocol that we built was the serial peripheral interface. As we can see a transaction of the protocol over here, we have the serial clock, the chip select, and the data out. There was testing conducted on multiple levels for these protocols. The first was simulation. Then we checked it on the oscilloscope, as we can see over here. And then we tested it with actual products. An example of this is the SPI receive test that we conducted. So we had a light sensor, and with ambient light, the readings that were recorded was 31. When torchlight was flashed onto this, we recorded the reading of 246, whereas the max possible was 255. We also built the UART protocol on this platform. For UART, we leveraged the Xilinx soft-core processor microblaze, which had the capability built in. We can see a transaction of 101011 on the scope shot. And the testing process was similar for this communication protocol as well.
So the inter-integrated circuit, or I2C, the communication protocol, was implemented using both VHDL and Verilog. We had a VHDL open source module for the underlying I2C data handling logic, and then the Verilog code that we had written was handling all the user control logic. So we were able to provide up to 3 messages in a single I2C transaction that are fully configurable with repeated start capability. As it says, it's SEA and SEL, so it's the data and clock line for the 2-wire I2C bus. And the line is held high by the FPGA by default, so if no device is driving it, it is held to VCC, as it should, for an I2C bus. So the testing for the I2C interface was performed in 3 phases. So initially, after simulation, we created a benchmark using a Raspberry Pi and some easily written software to communicate with this A to D D to A board that you can see pictured in the bottom middle. And so we would read in A to D data from it and then immediately send it back out using the code of the Raspberry Pi. We then ported that functionality using our VHDL and Verilog code to a Spartan 6 Basis 3 eval board and tested our functionality of our system using that and created the same test where we would read in data and then send it right back out. And then we finally moved that onto the KC705 evaluation board, which has a Kentech 7 FPGA. And we again performed the exact same test. So it required 3 messages in that transaction. First, you would read in the data, then you had to use a repeated start so that you could now write a control byte to the device, and then another write to actually send the data. Digital signal processing subsystem was implemented also using the microblaze soft core processor in the FPGA. All the FIR and IIR filtering was computed in Q15 fixed point format using just C implementations, direct linear convolution. We chose to implement it in C so that the user could provide header files of a specified format to change any filter coefficients that they might want for filtering.
So as you guys saw, there's quite a bit of different subsystems that do quite a lot of different things in our project. And in order to have control over all these subsystems in a central panel, we built a nice user interface. So here we have a very colorful user interface that was implemented in command line PuTTY shell. This right here is the main menu. And from here you could select to go into each subsystem to set up your test. And the user interface was set up in a way to make you fill out all your parameters for the forgetful engineer that might forget some things.
So this is a unique domain that we are playing with over here. We're not trying to compete against the oscilloscopes. They're beautiful, they're amazing, they're nailed down. And again, we're not trying to enter the domain of mass testing, custom-built equipment, which is used by test engineers and manufacturing engineers. This is a phase before data sheets are ready. So this is so that product engineers can actually make sure that the design is as expected and characterize the design as well as debug it if needed. So the UEP falls somewhere between basic lab equipment testing for the design and before the data sheet is ready on the product timeline. So this was our implementation. We also have a vision for this project. So we hope that this project is carried on, and some of the features we would like to include are a function generator, which would help send customized signals. And then we are also hoping that there could be an AI that could assist the engineers in debugging their products. And we were also hoping to have some LVDS support on the evaluation platform. So now we would like to proceed to demo our project.
Hey Sagar, how's it going?
I'm doing good, Frank. How are you?
Pretty good. So I came by to see how testing's coming along. Do you think you'll be able to meet the deadline?
Of course. Thanks to the Universal Evaluation Platform, testing and debugging has become a streamlined process. So we'll definitely be able to make the deadline.
Wow, Sagar. To be frank, that sounds great. I'll see you later. Good luck.
Thanks, see ya. Hi everyone, I'm excited to demonstrate our Universal Evaluation Platform to you. This tool has made my testing and debugging life very nice, easy, and almost enjoyable. Now let's take a look at this cool thing. So we have power supplies. The big board is fixed power supplies. The platform supports 5 volts, 3.3 volts, 2.5 volts, and 1.8 volts. For today's test, we'll be using the 3.3 volt fixed power supply. The small board over here is an adjustable power supply. This is great because you can programmatically change the voltage. So the range is from 0 to 4 volts, and we have a step of about 0.2 millivolts, which is great. The field programmable gate array is used to digitally communicate with the part that is being tested. This is the part over here that we'll be testing today. It's a D2A, A to D converter, and this little potentiometer can be used to change the analog inputs. Now let's take a look at our beautiful and elegant user interface. What you see over here is the main menu. To communicate with this part, I'm going to use a digital protocol called I2C. So let's go to the I2C submenu. It asks me to enter the address. I can perform up to 3 transactions. So first, I'm going to demonstrate the read. As we see, the data received was 105. Now let's tweak the potentiometer and see if this value changes. I just tweaked the potentiometer. Now let's look at the value, 38. This demonstrates that our I2C read works. Now I'm going to proceed to a write. Again, I go to the I2C menu. I enter the address, write. Now I'm going to perform 3 writes. The first one is going to be a control byte. Now I'm going to write 2 different data, and we'll be able to see them both on the scope. So I entered 90 and 223. This should give us different voltage outputs. Let's take a look at the oscilloscope. So as we see, we have different voltage outputs. Let's take a single sequence. And as we see, we can achieve 2 different voltage levels. Now, let's just try and get a single voltage output. Let's take a look. As we see, we have a great analog voltage. This shows that our D2A works and we can successfully write using I2C. As we see, this has simplified my testing life. Alright, thank you very much, and have a nice day.
Any questions?